Welcome to this Nexus tutorial. We will cover the log library following up the buck controller example. There are three types of logs that can be generated with the library. The simplest one is based on text messages and timestamps. Then there is also a graphic signal log functionality. And finally, HTML test report generation based on assertions. Logs can be generated as individual files for each process. But what makes it specially useful is the fact that it can create join logs from all the processes running together, called global logs. Let's get started by adding a global message log in our controller process. We will declare the message log as global. Then we just have to generate the messages from wherever we want. In this case, we will log every time a setpoint Ethernet frame is received. Now in the supervisor, we will do the same, declaring message logging as global, and generating a message every time it sends a new setpoint request. We will now add graphics logging. In the controller, let's make it global. Now we will call the graphics log step at every iteration of the main while loop. We are ready to configure the signals to log in our application. We will select the output voltage, output current, setpoint and integral part of the PI control loop, and finally pass them to the log library. They will be all logged every time the step function is called. Now in the supervisor, we will also make graphic logging global, and we will log the setpoint signal at every step of the while loop. Now and only in the supervisor, we will create a test assertion. We just have to add the construction of the message and call the assertion with the condition that the output voltage matches the setpoint with a 0.1 volt tolerance. For that, we will have to read the output voltage from the shared memory. We will also move the sync function to the beginning of the while loop to ensure that it is synchronized at time 0, and move the time increment to the end of the loop. Finally, we will decrease the time step to 50 milliseconds, and reset the set point to 0 after reaching 5 volts, so the results are more visual. In order to simplify launching the processes, we will create a YAML file to use with the launcher application. Let's edit the file with the commands needed to launch the executables. Now let's open the graphical interface of the launcher and load the YAML file. We will be able to launch the processes with one click. Let's open the simulation and launch it as well. We will be able to see what happens. Now that it has finished, the log files have been created in the project directory. We can see that the message log is a plain text file with a sequence of setpoint requests and receptions. We can identify the creator of each message by the slot number in brackets. The test report is generated in HTML. We can see that it is almost correct except for the corner cases where the duty cycle limitation doesn't allow the converter to work. Finally, let's open the graphic log. Using the KirLab Viewer application, we can drag the KNL file in it. Now we can explore the signals, accommodate the view to what we want to analyze and measure with the cursors. If you liked this video, hit the like button and don't forget to subscribe to this channel.